ሰላም ሰላም እንዴት ናችሁ? እንኳን ወደዚህ ቪዲዮ በደህና መጣችሁ። ዛሬ በድጋሚ ተመልሻለሁ። ዛሬ የተመለስኩት በቤዚክ ማትማቲክስ ፎር ናቹራል ሳይንስ ወርክሽት ሶሉሽን ይዤ ነው። ይህ ወርክሽት ቻፕተር 2 ላይ የተዘጋጀ ወርክሽቱ ነው። ስለዚህ ከዚህ ወርክሽት የተወሰኑ ሳምፕል ጥያቄዎችን ሶሉሽን አብረን ያለን ማለት ነው። ስለሆነም በቀጥታ ወደ ቪዲዮቹ ወይም ደግሞ ወደ ጥያቄዎቹ ከመሄዳችን በፊት ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ሰዎች ካላችሁ ቻናሉን ሰብስክራይብ በማድረግ እና ቪዲዮንም ላይክ በማድረግ እንድትጀምሩ አበረታታለሁ። በመቀጠል ወደ ጥያቄዎቹ እሄዳለሁ። የመጀመሪያው ጥያቄ using a principle of mathematical induction, we are asked just to prove 5n plus 5 less than or equal to n square for every n greater than or equal to 6. So in order to prove such a theorem or simple statement by using a principle of mathematical induction, we have steps. The base case, inductive hypothesis, and the last one is inductive step. So the first one, that is best case, could be just proving or checking the truthiness of the statement for the first few elements of n. In this case, the first value of n is 6, so that let us check for n is equal to 6. So directly, if we substitute 6 in the place of n, here we have 5 times 6 plus 5 is equal to 35, which is less than or equal to 36, which is 6 square. So it holds true for the first value of n, that is n is equal to 6. Then depending on the base case, the second step within this mathematical induction would be inductive hypothesis, that is simply assuming the statement holds true for an arbitrary natural number, that is k. So we must assume that 5k plus 5 is less than or equal to k for some k greater than or equal to 6. That means for an arbitrary natural number k, we have to assume that 5n plus 5 is less than or equal to this one, that is k square. Then based on this assumption, what we are asking, or simply what we need to show here, is that we must show that the theorem holds true for also for the next natural number, that is k plus 1. To do this, for k plus 1, if we directly substitute k plus 1 in the place of n, here we have this one, that is 5 into k plus 1 plus 5, which is equal to 5k. That is, if you distribute this 5 over k plus 1, you have 5k plus 10. And then, which is less than or equal to k square plus 5 from the hypothesis that already we have here. But in this case, we have still less than or equal to k square plus twice of k plus 1, because this one, that is twice of k plus 1, and because of this one, that simply is k greater than 6, 5 less than 2k plus 1. 5 less than or equal to twice of k plus 1, that is twice of k plus 1 is greater than or equal to 5, so that k square plus 5 is less than or equal to k square plus twice of k plus 1. Because of this one, that simply this 5 is less than or equal to twice of k plus 1. Then this one, that is k square plus twice of k plus 1, is a perfect trinomial, that is, which is the square of k plus 1 square. Therefore, if you observe a statement that is the form of this statement with k plus 1, 5 times k plus 1 plus 5. This is, which is the equivalent with, that means this is identical with k square plus twice of k plus 1, but this k plus 1, the whole square, is less than or equal to 5 into k plus 1 plus 5, so that it is true by using that of induction or simple mathematical induction. The statement holds true for n greater than or equal to 6. The next one, that is question number 2, that is question number 1b, will be again on principle of mathematical induction. Using principle of mathematical induction, prove that twice of n plus 1 is always less than or equal to twice of 2 the power of n for every n greater than or equal to 3. Again, we have to follow the previous 3 steps that already we have seen previously. So that in this case, and the first step would be checking that is the best case. The best case, that's simply for the first value of n here is 3, so that we have to check whether this statement is true for n is equal to 3. So directly substituting n in the 3 in the place of n here, we have twice of 3 plus 1 is equal to 7. Again, this 7 is less than or equal to 8, which is 2 cubed. So that the statement holds true for n is equal to 3. Then after checking this one, we have to proceed to the inductive hypothesis. The inductive hypothesis is simply assuming that the statement holds true for an arbitrary natural number which is greater than or equal to this one, that is 3. So that's, let's assume that twice of k plus 1 less than or equal to twice of k for some k greater than or equal to this one, that's simply 3. Then based on this assumption, the next or simply the next step would be inductive step, which is checking for the truthiness of this statement for k plus 1 or the next natural number that is k from this assumption. Then directly, if we substitute k plus 1 in the place of n, here we have twice of k plus 1 is equal to twice of k plus 3. This is twice of k plus 3. So if we factor out this one, that is twice of k plus 1, that is dividing this one, that's simply 3 into 2 parts 1 and that of 3, that is 1 plus 3, we have this one. Then this one, twice of k plus 1 plus 2 is less than or equal to twice of k plus 2. By the hypothesis that simply here what we have here is twice of k plus 1 is less than or equal to twice of k. So that we have twice of k here plus 2 here. Therefore, there is less than or equal to twice of k plus twice of k. Since twice 2 is less than or equal to the power of k for k greater than or equal to 1. Then if we factor out to the power of k the common factor we have, or simply this one, that's simply twice of k. His identical is twice of k plus to the power of k plus to the power of k, which is yeah, 2 times to the power of k plus 1, which is to the power of to the power of k plus 1. Therefore, there is the last one, that's simply by using the mathematical principle of mathematical induction. The statement that is to the power of n plus 1 less than or equal to the power of n holds true for every n greater than or equal to 3, because directly we are assuming for the statement is true for k, or an arbitrary k, so that we are able to show that the theorem holds true for the next natural number that is k plus 1, so that is the approach. The next one, that is question number 2a. Find the LCM of the smallest one-digit composite number and the smallest two-digit composite number. You know that the LCM of the given any two or more natural numbers will be obtained by either prime factorization method or listing method. But here, in this case, we are not directly or simply explicitly given the given digits or simply numbers. What we are given here is we are given the smallest one-digit composite number and the smallest two-digit composite number. So we have to know these to first just before we try to calculate their LCM. We know that the smallest one-digit composite number is 4. There is no any other one-digit number which is less than that of this one, which is a composite which is less than that of 4. And the smallest two-digit composite number is said to be 10. Therefore, we are asked just to calculate the least common multiple of these two. The least common multiple of these two could be just the, I think, this one that's simply 20, because the is 2 square and this one is 2 times 5. So that from 2 square we can take that is 2. And that means the highest one, that's simply 2 square, and from 5, even though it's not a common factor, we have to take, so that 2 square times 5 becomes this one, that's simply 20. Therefore, the least common multiple of a one digit, the smallest one digit number and the smallest two digit number, that is 4 and 2, is exactly 20. The next one, that is question number 2b, is this problem, that is, it says a factory produces two products, one every 9 minutes and the other every 12 minutes. If both products are produced at the same time, how long will it happen? So that means we are asked just to find the time taken for the two factories, or simply the factory produces the two products at the same time. Therefore, let us assume that the products are A and B. So that product A, the first product of the factory, is produced in every 9 minutes. And second product, that simply if it is product B, it is produced in every 12 minutes. So we are asking the time elapsed or simply taken or needed just to produce or simply to take out the two products and that of B at the same time. And therefore, these two products are like this. Therefore, their products, or simply the time taken just to have both the products and that of B at the same time could be just their LCM. That is the least common multiple of the time taken just to produce the individual products and that of B, that is 9 and 12. This is 36. So that we need 36 minutes, or just after the factory starts producing the two products in every 9 and 12 minutes, at the 36 minutes, both and that of B will be produced at the same time. So therefore, እዚህ ጋር ምን ማለት ነው? ይሄ የመጀመሪያው ፕሮዳክት ኤ ልክ በ36ኛው ማለት አራተኛ ፕሮዳክት ወይም ደግሞ አራተኛ ኤ ፕሮዲውስ ሲሆንና ሁለተኛው ፕሮዳክት ቢ ደግሞ ሶስተኛው ፕሮዲውስ በሚሆንበት ጊዜ ለዚህ አራተኛው ለዚህ አራተኛውና ሶስተኛው ፕሮዳክቶች ወይም ደግሞ እያንዳንዳቸው ኤ እና ቢ በተመሳሳይ ጊዜ ፕሮዲውስ ይወጣሉ ማለት ነው። So that is the application of least common multiple. Okay, the next one is question number 2c. A school has 45 boys and 60 girls. The principal wants to divide into the largest possible equal groups containing both boys and girls. How many students will be in each group? What we are given here is, we are given pupils or simple schools, boys and that of girls, which are 45 and 16 respectively. And the principal of the school wants to divide this into the largest possible equal groups containing both boys and that of girls. Then how many students will be in each group in the question? So that there is again the application of a greater common factor. So that at the greater common factor of both the boys and the given number of girls, that will be the maximum, or simply the largest possible equal groups containing boys and girls. So that the greater common factor of 45 and 60 is 15. So that the largest possible equal groups containing boys and that of girls will be this one, that is 15 students. That means the largest equal group contains 15 students each. So that the next one is question number 3, which is about an upper bound and lower bound of a given set or simple interval. We are given that we are asked just to find the least upper bound and the greatest lower bound of this interval. This is an open interval which starts from 0 and goes to that of negative infinity. So that in order to do this, in order to calculate the bounds, we know that a certain point or simply real number is said to be the upper bound of the given set if and only if that number or simple real number is greater than or equal to that of every element of this set. So that any real number which is larger than that of every element of this set is said to be an upper bound for this set. Similarly, if there exists a certain real number which is less than or equal to every element of this set, so that that element is said to be the lower bound of this set. And that, by using that of completeness property, we know that if the set, or simply for any set which is a subset of set of real number, if the set has an upper bound, it must have least upper bound. If the set has lower bound, so that it must have greater lower bound. So that's it. Therefore, because this set is not bounded from below, but it is bounded from above, so that the set will have only an upper bound. Therefore, the upper bound of A could be a set that is simply x greater than or equal to that of there, including the even. But it doesn't have a lower bound because it is unbounded from below. Because we don't know the smallest possible element of the set, so that it is unbounded from below. Therefore, it will never have lower bounds. If the set doesn't have a lower bound, it will never have greater lower bound too. Therefore, the least upper bound for this one could be, that means the smallest element of its upper bound is, the upper bound is x greater than or equal to 0. The smallest element is 0, so that the least upper bound of this set is 0. But by using that of completeness property, since the set doesn't have a lower bound, therefore it will never have greater lower bound. That means the greater lower bound of the set doesn't exist. The next one, that's question number 3e. Again, it is on least upper bound and greater lower bound of a given set. We are given the set that simply set A in the form of this function that is 3 minus 1 over n, where n is an element of n, set of natural number. That means, so that we are asked just to find the least upper bound and the greater lower bound of the set. First, in order to determine the least and greater lower bound of the set, we have to know the property of the elements of this one. We know that when n is equal to taken to be the first natural number, that is 1, 3 minus 1 over 1, or simply 1 would be this one, that's simply 2. So that they hit the first element for this set, that's simply set A. Then the next one could be when n is equal to 2, 3 minus 1 over 2 could be 5 over 2. When n is 3, 3 minus 1 over 3, it becomes 8 over 3, which is an increasing because this is decreasing when n goes to, when n is increasing. Therefore, most probably when we assume that n is a very large positive natural number, so that 1 over n will tend to 0, and the whole expression of this formula, that is 3 minus 1 over n, will approach to 3. Therefore, every element of this set will be bounded in between 2 and that of 3. Therefore, the lower bound of this set, that's simply set A, that is a real number which is less than or equal to that of every element of this one could be x less than or equal to 2, and its upper bound will be the set containing x greater than or equal to 3. So that since this set has both an upper bound and lower bound, therefore it will have its own least upper bound and greater lower bound. so that the least upper bound of the given set could be, because the greater lower bound of this one is that simply x greater than that of 3, so that the smallest element within this set is taken to be the least upper bound of the given set E. And the greater lower bound could be the greater lower bound of the lower bound of the set that simply set E is x less than or equal to 2, so that from the set the largest or the greatest element could be taken as the greater lower bound of this one, so that 2 is the largest element, therefore the greater lower bound of the set could be 2. Next, question number 4. We are asked just write the complex number that is on the set of complex number 2 plus I multiplied by 3 minus 2i divided by 1 plus I in the form of x plus y, that is in standard form. Therefore, our first thing would be multiplying the denominators together. When we expand this one, that is simply 2 plus I times this one, that is 2 times 3 is 6, 2 times minus 2 is minus 4i, I times 3, that is plus 3i, I times minus 2i could be, and that is, I think positive 2, that is I square is minus 1 times minus 2 is positive 2. So that when we simplify this one, we have 8 minus I, which is the denominator. Now let's divide this one, that is 8 minus I by 1 plus I. When we do this, that is in order to change this one into x plus y form again, we have to multiply both the numerator and the denominator of this fraction by the complex conjugate of this one, that is 1 minus I. So that we have this one, that is the product of 1 plus I and 1 minus I could be the square of the norm of this thing, so that it is 2. But this could be, that is the denominator, the product, that is when we expand it, we have this one, that is 7 minus 9i. We have the denominator, that is 2 here. Therefore, the standard form of this simplified form of this expression could be this one, that is 7 over 2 minus 9 over 2i, so that the real part, that is simply the value of x, and minus 9 over 2 could be the imaginary part of the simplified form of this complex number, which is this thing. The next one, that's question number 4c. Again, it is simplification of complex number, writing this expression in the form of x plus iy form again, that is in standard form. So if we follow the same procedure, the solution could be, first, let's take the cube of I, that is pure imaginary complex number. I cubed is simply I squared times I, that is I squared is minus 1 times I could be minus I. And let's again expand the numerator, that's simply 2 plus 2i times 1 minus I multiplied by I over I, that is the complex conjugate of this one, so that it is just 3 plus twice of I into 1 minus I over minus I square. This is, I think, this one, that simply this would be further simplified to this thing, that is 3 plus 3i plus 2i plus 2i square. Then the 2i square is minus 2, because I square is minus 1, minus 1 times 2 will be minus 2, so that if we combine these two, we have 3 minus 2, that is, I think, 1, and 3 plus 2i could be, that is 5i, therefore 1 plus 5i, the simplified form of the given complex number. So that the standard form of this expression could be 1 plus 5i, where 1 is the real part and 5 is the imaginary part of this simplification. The next one is question number 40. It says write the following complex number, the complex number in power form, in a standard form, that is x plus I y form. So that the solution will be, first we have to convert this one into polar form. That is, a polar form of a complex number means writing the given complex number as a function of r in theta. We know that first the r, that is the magnitude of the complex number, could be the square root of the square of the imaginary part plus the real part of the complex number. That is, the real part is radical 3. It is a square plus minus 1, which is the imaginary part of this one, that is this one, that's simply 2, which is the square root of 4. And the argument that simply theta could be tan inverse or arctan of the imaginary part divided by the real part, that is minus 1 over radical 3. And this could be a negative angle, which is negative pi over 6. So that if we can obtain a range that of theta, we can write this one in the form of that of polar form as using this one, that's simply de Moivre's formula or simply theorem. We have to the power of 10, that is the power of this one, and that is r to the power of 10. That means then cosine of 10, the exponent multiplied by theta plus I times sine of 10, that is 10 is this one, that's simply the exponent multiplied by this one. Then when we further simplify this thing, we have to the power of 10 is, I think, about 1024. Then cosine of the product of these two, that is negative 5 over 3, 5 pi over 3, plus I times sine of negative 5 pi over 3. Therefore, this is the standard form of this thing. So that in order to determine x here, x means 1024 multiplied by cosine of pi over 3. And y means that is the imaginary part of this one could be 1024 multiplied by sine of pi over 3. Sine of pi over 3. Then the next question is 5a. That is, we're asked just to solve the complex number z is equal to x plus iy. That is what we're given here is 4 plus 5i is equal to z minus 1 minus I. So that we are asked just to find the value of z which can make this equation to be true. Or just we are asked just to write z in terms of this one, or simply in standard form as in the form of x plus iy. So the solution will be just transferring or simply taking this one to the left of the equality sign, so that we have z is equal to 4 plus 5i, then plus 1 minus 4 I, and 1 minus I. That is the summation of two complex numbers. We know that in order to add two complex numbers, the sum of any two complex number is complex number, and it could be obtained by adding their corresponding real parts together and the imaginary parts together. So that the sum of these two complex numbers could be, that is 4 plus 1, that is the real part of the first, plus the real part of the second complex number is 5. And the sum of the imaginary part of this one, 5i plus minus I, could be this one, which is 4i. So therefore, z could be z could be 5 plus 4i. The next one, that is question number 5c. Again, it is solving this expression, this equation involving complex number in the form of z is equal to x plus iy. We have 3 plus 5i plus x minus iy is equal to 6 minus 2i. So in order to have this form, that is z is equal to x plus iy, we have to equate the imaginary and the real part of the given complex number. We have the real parts here, and the real parts could be the we have 3 here, x and 6, so that the sum of these two must be identical with the real part of the x plus iy, that is simply x, so that 3 plus x must be equal with this one, that is 6, which implies x is equal to, because it is linear, that the value of x will become 3. Similarly, from the imaginary parts, we have 5 here, minus the second imaginary part of this one, that's simply y, is equal to this one, that's simply minus 2. Therefore, here the value of y could be, that's taking this one into here and taking minus y to the left of the right of this one, so that we have y is equal to 7. Therefore, the function, I mean the complex number that z could be in the form of x plus iy. That means the value of x is 3, the value of y is 7, so that it becomes z is equal to 3 plus 7i. Question number 6b. For the values of a real number x and y such that the complex number 3 minus ix squared y and minus x squared minus y minus 4i are conjugate to each other. So what we are asking here is we are asking just to find x and y where these two complex numbers are. One is the complex conjugate of the other. That means you know that the complex conjugate of a given number or simply complex number is obtained by taking only or making the imaginary part of the given complex number to be a negative one, or its opposite. So that if z is equal to plus iy, that is, it is complex conjugate will be this one, that is a minus pi. Then 3 minus ix squared y is equal to, that means minus x squared minus y minus 4i, because if this one, that's 3 minus ix squared y, and this complex number are one is the complex conjugate of the other, so that in order to make equal, the complex conjugate of either of these two must be identical with the next one. So therefore, if we take this one, this is complex conjugate. Again, if we take the conjugate of the complex conjugate, it must be identical. That's simply the double conjugate. So that must be minus x squared minus y, just taking this one to be the opposite, plus 4i. And then equate the real and imaginary parts together. That is this expression and this one. We have the real part for this one is 3. The imaginary part is x squared y. The real part for this one is minus x squared minus y, and the imaginary part is 4. So if we equate this expression, we have this one, that's 3 is equal to this 3 is equal to minus x squared minus y, and the imaginary part of this one, that's minus x squared y, is equal to this one, that's simply 4. Then if we simultaneously solve this thing, we have this one, that is y is equal to minus x squared, that is minus 3, and this one, that is just rewriting this one another way of writing, so that the solution will be that is, for example, if we let this one, that is because x to the power of 4 plus 3x squared minus 4, if we let by using that substitution, that is let, for example, x squared is equal to a. So if we substitute x equal to a, we have a squared plus 3a squared minus 4. Then it becomes simple quadratic equation. We can have a solution there. The solution, I think the solution becomes 1 and that of minus 4. So we have to ignore minus 4, because the square of the square of a can never be identical with minus 4, so that then we have to take the positive part, that's simply 1, so that a square is equal to 1 and x is equal to plus or minus 1. Then if x is plus or minus 1, for example, if x is 1, what will be y? If it is minus 1, if x is minus 1, for example, one of the possible values of x which is obtained here, and if we replace it here in the place of x here, so that we have minus of 1 squared, that's simply minus 1 minus 3, which is minus 4. Even if we take minus 1 again for x, it is still minus 4, so that the values of x and that of y, which can make this complex number to be the complex conjugate of this one, or vice versa. That is when x is plus or minus 1 and y is equal to minus 4. So that this is the solution. The next one is question number 6, which is we'll find the values of the real numbers x and y such that x over 1 plus I plus y over 1 minus y is equal to 1. Again, solving the values of x and y, which can make this equation involving complex number to be true. The solution will be multiply by conjugates of each. That means in order to write each complex number in standard form, we have to multiply, for example, x over 1 plus I by the complex conjugate of 1 plus I and y over 1 minus 2i by using the complex conjugate of this 1 minus y, which is 1 plus y. So that becomes x into 1 minus I over 2, where this is to be because the complex conjugate of this number and this one is already 2. Similarly, for the next one, we have y into 1 plus 2i, that is the complex conjugate of 1 minus 2i over 5. This 5 will be obtained by taking the square of the real part of this 1 plus the imaginary part of this complex number, which is 1 plus 4, that is 5 is equal to 1. Then the next one could be, in order to further simplify again, let us multiply both sides of this equation by the least common multiple of 25, that is simply by 10. When we do this, we have 5x into 1 minus I plus twice of y into 1 plus 2i is equal to 10. Then, in order to determine the y and that of x, we have to equate again the real and the imaginary part of this expression. So we have this equation that simplifies x plus 2i, that is the real part. The real part from the first one is 5x times 1, that simplifies x plus 2y times 1 is equal to the real part is this one, that's simply 10. And the next one, that is the imaginary part, will be minus 5x plus 2y times 2, that's simply 4y. But the imaginary part to the right of the equality sign is 0, therefore it is 0. Then when we solve this one simultaneously, if we directly add them together, 5x, we have 5x, it becomes 0, this is 6, and this could be 10, so that 6y is equal to 10, that is, I think, 5 over 3, or yeah, y will be 5 over 3. Then if we obtain one of these two, that's simply y. By back substitution, we can determine the second value, the value of the second variable, that is x. Therefore, the solution for this system of linear equation could be x equal to 4 over 3 and y is equal to 5 over 3. Therefore, when x and y are given here, this equation that simply will become satisfied. Will become satisfied, or the sum of these two will becomes 1. The next one is question number 6D. Again, find the values of the real numbers x and y, say that's x over this plus yi over 3 plus I is equal to 2 over 1 plus I. A similar procedure from the previous one with a little complexity here. So the solution could be, first, let us simplify each term. That means let's write each of the three terms in a standard form, that is z is equal to x plus iy form. So that just to do this, we have to multiply the first fraction by using the 2 plus y, that is 2 plus I, which is the complex conjugate of this one, and this must be multiplied by 3 minus I, and this one 1 minus I. When we do this, we have x into 2 plus y, 2 plus I over 5. This 5 will be obtained by adding the square of the real part of this one and the imaginary part of this one, that is 4 plus 1. And this could be obtained by adding the square of 3 and 1. And here, that is, I think there is 1 minus I over, that is 2 into, it must be 2 into 1 minus I over 1 square plus, that is 2, but these 2 can be cancelled by 2, and we have left only this one, that is 1 minus I. And then if we multiply again both sides by the least common multiple of 5 and 2, that's simply by 10, we have 4x plus y. if we multiply this one by 10, that means we have 2 times twice of x times 2, that's 4x, twice of x times y, I could be this one, that's simply and then this is y plus, that is after multiplying, we take the real parts together and the imaginary parts together, we have this one, that's 4x plus y, the real part of this expression to the left of the equality sign, and twice of x plus 3y times I will be the imaginary part. And on the left, if we multiply both sides by 10, we have 10 minus 10i. Then let's equate as usual the real and the imaginary parts together. So that the from the real part, that's simply the real part of this complex number is 4x plus y. It must be identical with 10. And the imaginary part 2x plus 3y must be with the imaginary part of this one, which is minus 10. Therefore, solving this system of linear equation, we have the solution that is x equal to 4 and y is equal to minus 6. That means when x is taken to be 4 and y is equal to minus 6, this expression or simple statement or equation will become satisfied. So that the exact values of x and y satisfying this condition or simple equation could be 4 and minus 6 respectively. The next one is question number 7. We are asked just to find the values of the real y such that 3 plus 2i plus times 1 plus iy is in the first case real, that is real without complex, without imaginary part or simply whose imaginary part is 0, and second one is purely imaginary number with 0 real part. That means for the first one, first we have to expand this one and write the product of these two complex number in standard form, that in the form of z is equal to x plus iy. So that when we expand this one, we have this one, that's simply 3 minus 2y plus I multiplied by 3y plus 2. So that this is the real part, and this one is the imaginary part of the simplified the product of these two complex numbers. Therefore, what we are asked here is in the first case, we are asked just to determine the possible value of y which can make this complex number to be real. That means which can make the imaginary part of this complex number, that is 3y plus 2, to be 0. That means the complex number will become real whenever it is imaginary part is 0, and the complex number is said to be purely imaginary number whenever it is a real part is 0. So that when we equate in the first case, that's simply for just to make this one real, we have to make this imaginary part to be 0, so that that means real when the imaginary part is 0, so that the imaginary part is 3y plus 2 is equal to 0, so that y is equal to minus 2 over 3. Therefore, whenever y is equal to negative 2 over 3, this complex number will be real without imaginary, or its imaginary part will become 0. Just to make it is imaginary, we have to make the real part to be 0. The real part is 3 minus 2y. So that when it is 0, y must be 3 over 2. Therefore, whenever y is equal to 3 over 2, this complex number will be purely imaginary number or simply imaginary complex number. Okay, that's it. The next one, question number 8. A, given z1 is equal to this one and z2, and we are asked just to find the modulus or the norm of z1 plus z2. We can approach different approaches or simply procedure for finding this one, but let us see how we can find the norm of z2, the sum of these two complex number. First, let's add them together. That is z1 plus z2 is equal to the absolute value of 2 plus 3i, that is simply for z1, and 3 plus 2i for z2, which is equal to 5 plus 5i. Then the norm of the sum of these two is said to be the norm of their sum, that's 5 plus 5i, and this could be the square root of 5 square, that is the square of the imaginary and the real part of this complex number, that is 5 square plus 5 square is 50. And when we further simplify this one, it could be 5 radical. Therefore, the sum of these two could be 5, a real part of this complex number, that is 5 square plus 5 square is 50. And when we further simplify this one, it could be 5 radical 2. Therefore, the sum of these two could be 5 radical 2. Separately, it is all, I think it is also possible just to find the sum of the individual complex numbers, the norm of the individual complex numbers, and add them together. Okay, the next one could be, given z1 is equal to this one, we have 3 complex numbers. Then after we are given these 3 complex number, we are asked just to find w in terms of a and b in the form of x plus ii, where w is equal to z1 times z3 over z2. Just simplification. So to do this, first let's find z1 times z3. Or let us substitute that simply z1, z2, and z3 like this. And we have this one that's simply 2 plus 3i. That is z1 times 3 plus 2i multiplied by this one over this. That means this could be just to make this one simply just to live, or just to make this one into real, we have to multiply both the numerator and denominator of this one by the complex conjugate of this one. So that is this fraction. Then this could be, after simplifying this one multiplication and this one even, and further simplification we have, we can obtain this one, that is w is equal to 6a plus 4b over 13 plus 5a minus 12b over 13. So that this one 6a plus 4b over 13 is said to be the real part of w, which is z1 times z3 over z2, and 5a minus 12b over 13 is said to be the imaginary part of this one, that's simply w, when w is z1 times z3 over z2. The next one, the next question is question number 8c. That means just finding the argument of w in radian measure whenever w is given to be 17 over 13 minus 7 over 13. We know that the argument of a given complex number is obtained by the tan inverse. That we know that the argument of a given number is, or simply complex number is, it is an angle which is formed in between the positive x-axis and the axis, or simply the arrow determined by the complex number itself. Therefore, this is an angle that simply, if the angle is that one, then it could be arctan, or simply tan inverse of the imaginary part of the complex number divided by the real part of the complex number, that is minus 7 over 13 over 17 over 13. So that this could be tan inverse or arctan of negative 7 over 17, which can be approximated to negative 0.391 rad. This is negative because this is something, the angle that is the terminal side of the angle will be found in the fourth quadrant, so that because the argument is an angle between the positive x-axis and the axis, or simply the array of the complex number itself, so that it is the negative angle. The next question, question number 9. Find the modulus and argument of z, w, zw and z over w if z is equal to 1 plus I and w is equal to radical 3 plus I. And you are asked just to put your observation at the last. And therefore, here, what we are given here is we are given about two complex numbers z and w, and we are asked just to find the modulus and argument. We know that the first the modulus, I mean the modulus, yeah, the norm of z is equal to radical 2, which is the square root of 1 square plus it is imaginary part, that's 1 square. And its argument will be tan inverse of 1 over 1. That's simply tan inverse of 1, which is pi over 4. Similarly for w is given to be radical 3 plus I, so that it is norm or simply modulus could be the square root of the radical 3 square plus 1 square, which is the square root of 4. That's simply 2, since norm is positive. And its argument will be that's the angle between the positive x-axis, and its array will be tan inverse of 1 over radical 3, or arctan of 1 over radical 3, which is pi over 6. And their product, that simply z times w could be, that is their norm first. The norm will be, that is 2 radical 2, which is the product of norm of z times norm of z. And its argument, or simply will be the argument of the product of two complex numbers, is simply the same as the sum of the arguments of the individual complex numbers, so that pi over 4 is the argument of z and pi over 6 is the argument of w, so that it is just 5 pi over 2. Similarly, the last one, z over w, that is first the norm could be radical 2 over 2, so that this radical 2 over 2 means the norm of the quotient of two complex numbers is said to be the quotient of the norms of the individual, so that radical 2, which is the norm of z, and 2, which is the norm of w, so that it is just radical 2 over 2. And the argument is also what? The argument of the quotient of the complex number is the same as the argument of z minus the argument of w. So that is just equivalent with, sorry, pi over 6. I think this must be minus. That means this is not, this is minus pi over 6. So that in this case, we have the difference between these two, which is pi over 12. Pi over 12, so that this is the difference. Therefore, what we can observe here is that the modulus and argument of the product of two complex numbers is here to be the product of their corresponding norms, and their argument is the sum of the individual complex numbers. And for the quotient, the norm of their quotient is the quotient of the individual norms, and their argument will be the difference between the arguments of the two. Question number 10. The complex number z is defined as z is equal to I into 1 plus I multiplied by 1 minus 2i square. It is further given that z, the complex conjugate of z minus 3i plus p of z minus 3i is equal to k of z bar, where p and q are real constants. Find the values of p and q. That means we are asked just to find the values of p and q, which are real constants satisfying this conditional simple equation. That means. So first let us compute z. Z is given to be here. So let us multiply z, simplify z, so that z is equal to the simplified form of this expression, which is directly taken from this one, and it could be 7 plus I. When we simplify this one, that's simply squaring. After squaring it, if we multiply 1 plus I with 1 minus y squared, it is exactly 7 plus I. Then given equation, more simple equation that simply if we substitute it here, we have 7 plus 2i plus p of 7 minus 2i is equal to q of 7 minus I. Q of 7 minus I means the complex conjugate because it is z bar, z this one, so that it becomes 7 minus I. And this could be 7 plus 2i could be, when we substitute z that is 7 plus I here, we have the imaginary part of this one is that simply, I mean the real part is 0, so that we have 7 here. Then we have I here, I minus this one that's simply 3. After taking that simply it becomes a minus 2 and its complex conjugate could be positive 2. Then after writing this one, we have the following system of equation that is from equating its real and imaginary parts. From the real parts here, we have the real part from this one, that's simply 7 plus 7p is equal to 7q. And from the real part, we have twice of I minus twice of p. When we distribute this one over here, it is just minus q. Then solving this system of linear equation, we have the values of p and q, that is simply p is equal to 3 and q is equal to 4. Then whenever p is equal to 3 and q is equal to 4, this equation that is z minus 3i bar plus p of z minus 3i becomes q of z bar when z is this expression or 7 plus I. The next one is question number 11. Again, it is solving, that is for find the element of the complex number in the form of x plus iy, where z bar is equal to x minus iy if z is equal to, I mean z minus 8 is equal to I into z minus twice of z bar. Then in order to write or simply have a solution for this one, let z is equal to x plus y, so that its complex conjugate would be x minus iy. And then, sorry, x minus 8 plus iy is equal to 8y minus ix. That means if you substitute this one, that's simply, we have z minus 8, we have this one, that means, so that it becomes x minus 8 plus iy is equal to y minus ix. Then equating the real and the imaginary parts as usual. We have the real part of this one is x minus 8, and the real part of second one is 8, so that we have x minus 8 is equal to y, and the imaginary part will be, that is y is equal to this one, that is minus x. So that's solving the system of linear equation. We have x equal to 4 and y is equal to minus 4. That's just if you substitute minus x in the place of y here and take to this one, it becomes 2x is equal to 8. Dividing both sides by 2, we have 4 for the value of the first variable x. And after obtaining this one, one is the negative of the other, so that if x is 4, y becomes negative 4. Therefore, after obtaining this one, the form of the complex number could be z is equal to 4 minus 4y, that in the form of x plus iy. Question number 12a. Express the following complex number in polar form. Polar form, that means writing the expression or simply the given complex number as a function of r and theta, where r is its modulus and theta is the argument. Just to do that, first we have to simplify this one or convert this one into standard form of complex number, that is z is equal to x plus iy. Then when we simplify this one, that is 3 minus I over 2 plus I. When we multiply both the numerator and denominator by the complex conjugate of 2 plus I, that is 2 minus I, we have 1 minus I. Then when we square it, that means the square of this one, 1 minus I is equal to minus 2i. So that let's write this one into polar form. In order to write the polar form of this expression or simply given complex number, we need to have two things that simply the norm that is r and the argument that's simply theta. Simply the r could be the square root of, since the real part is 0, that is the square root of minus 4 square, that is 4, which is 2. And theta could be, that is tan inverse of minus 2 over 0, which is undefined. Whenever tan inverse of, we know that tan inverse of an angle theta is undefined, whenever theta is either negative pi over 2 or pi over 2. But in this case, it is negative pi over 2 because the terminal side of this one, or simply this point, is found on the negative imaginary axis. So that theta is negative pi over 2. Therefore, using this one, the polar form of the given complex number could be 2 times, that's simply r, cosine of negative pi over 2 plus I times negative sine of negative pi over 2. So that this is the polar form of the given complex number. Next one is express the following complex number in polar form. Again, that's the same, but with a little modification or simply complexity here because of the existence of this one, that simply the square is just the denominator. So as usual, first let us simplify this one, this expression or this complex number in standard form. When you do this, first we have to simplify the denominator. So that 1 plus 7i over 3 minus 4i, that is the square of 2 minus I is, I think, 3 minus 4i. And then when we multiply again this one both sides by the complex conjugate of this one, we obtain minus 1 plus I. So that the polar form will be, as usual, as we have seen previously in the previous question, in order to write the polar form of this complex number, we have to determine its modulus and the argument. The modulus is the square root of minus 2 square plus 1 square. I think that's radical 2, and its argument will be tan inverse of or arctan of 1 over minus 1 or simply minus 1, which is negative, that is simply negative, positive 3 over 4, which is in the second quadrant. Therefore, r is this one, theta is this one. Therefore, the polar form of this complex number could be radical 2, which is r, cosine of 3 over 4, that is the argument, plus I times sine of 3 pi over 4. Therefore, this is the polar form of this expression or its simplified form, which is minus 1 plus I. Okay, the next one, that's question number 13a, is finding the argument and the principal value of the argument there. We know that the argument is the angle between the positive x-axis and the terminal side determined by the complex number itself. So that to do that, first we have to simplify this expression. That is, we have to change it into a standard form, that is, which is suitable for knowing its real and imaginary part. Therefore, the simplified form of this one, that is when we multiply both the numerator and the denominator by the complex conjugate of the denominator, which is 1 minus y, that is 1 plus 2i. We have this one, that is 7 minus I over 5. This is 5 because it is the square of the norm of 1 square minus 2 square, or the product of this complex number by its complex conjugate. And then the principal or simply the argument could be, that is arctan or tan inverse of the imaginary part of this one, that is minus 1 over 5 divided by 7 over 5, which is minus 1 over 7. And this could be approximated using that of calculator, scientific calculator. We can approximate this one as negative 0.1419 rad in radian measure. That means this is for the quadrant angle. That is why it is negative. And the next one, that's question number 13b. Find the argument again and the principal value of this one, that's simply this expression. As usual, let's first simplify it. So that the simplified form of this thing could be, that's minus 2. That means we have to change first individually the fractions into standard form, and when we add them together we can obtain minus 2i. So that the principal or the principal value or the argument of this one could be tan inverse of negative 2 over 0, because the real part of this simplified form of this expression is 0. So that the argument that simply theta could be negative pi over 2, which is a negative angle. So that this could be approximated as negative 3.14, which is negative 3.14 over 2, something like that. You can approximate it, or even we can put it like this in radian measure. Next is the same question, that finding the argument and principal value again. Again, we have to multiply or simply simplify first. The simplified form could be this one, that is 1 minus radical 3i times 1 minus I could be this one, that is 1 minus radical 3 minus 1 plus radical 3i. That is, this is the real part, and this one is the imaginary part of the simplified form of this expression. Therefore, the argument or the principal argument of this one could be tan inverse of negative 1 plus radical 3 over 1 minus radical 3, which could be approximated as 5 pi over 12 rad. I can use scientific calculator. That is tan inverse of 1 plus radical, negative 1 plus the negative of 1 plus radical 3 over 1 minus radical 3 is 5 pi over 12 rad. The next one, that is we are approaching to the need. Proof using de Moivre's rule, theorem. Cosine of 2 theta plus I times sine of 2 theta over cosine of 3 theta plus I times 3 theta is equal to cos theta minus I sine theta. So to do this, we have this one, that is the first one, or simply denominator, cos 2 theta plus I sine 2 theta, means using de Moivre's or simply Euler formula, we have cos theta plus I sine theta, or simply z square. If we take z is equal to cos theta plus I sine theta, I sine theta, and the denominator could be cosine of theta plus I sine theta, the power of 3. Then when we take this one, that's simply minus this one, that's simply 2 minus 3, we have cos theta plus I sine theta, the power of minus 1, which is equal to 1 over cosine of theta plus I sine theta. Then when we change or simplify this one in standard form, we have to multiply the numerator and the denominator of this one by the complete conjugate of cosine of theta plus I sine theta, so that it is just cosine of theta minus I sine theta, because the complete conjugate of cos theta plus I sine theta, when we multiply this one denominator by 1, it is just this one, and cosine of theta plus I sine theta multiplied by the complete conjugate of this one could be, that is cos square theta plus sine square theta, which is 1, trigonometric identity. So that becomes cos theta minus I sine theta over 1, or cos theta minus I sine theta. Therefore, and this is how we can approach just to prove this expression. The next one is similar to the previous one, I guess, again on the application of de Moivre's theorem. That is proof using de Moivre's theorem that cos 3 theta is equal to cos cubed theta minus 3 cos theta times sine square theta. So just to prove this one, we have to expansion of this one, that is a plus cubed. A plus b cubed is equal to a cubed plus 3a square b plus 3ab square plus b cubed. So let us expand this one, that's cos theta plus I sine theta, the power of 3. This could be the cubed of the first one, that's cos cubed theta, 3 times a square, that's cos square theta, multiplied by b, that is simply I sine theta, so that's 3i cos square theta sine theta minus y minus here, because 3a means a is b, so that's 3 times cos theta, but b squared, that is when the square of I sine theta could be the square of I is minus 1, sine theta is sine square theta, so that minus 3 cos theta times sine square theta minus I sine cubed, that is the cube of I sine theta, the cube of I is minus I, the cube of sine theta is sine cubed theta, therefore there is cos cubed theta plus 3i cos square theta sine theta minus 3 cos theta sine square theta minus I sine cubed theta. Then the real part of this one could be, that is cos 3 theta, that is the real part. Cos 3 theta is equal to, from this one, the real part of this expression, that is we have cos cubed theta plus, minus 3 cos theta sine square theta, but the rest, this and this one, that is I sine cubed theta, are imaginary. Therefore, cos theta could be cos cubed theta minus 3 cos theta sine square theta. Therefore, this is the proof. Question number 14c, prove using de Moivre's theorem again. Z to the power of n plus 1 over z the power of n is equal to 2 cosine of n theta, where z is equal to cos theta plus I sine theta. So if we are given z is equal to z to be this one, so that z to the power of n, by using that of the formula, we have z to the power of n is equal to cos n theta plus I sine n theta. Similarly, 1 over zn could be 1 over zn means 1 over z to the power, z to the power of minus n. If we substitute minus n in the place of n here, we have cosine of minus n theta, but since cos theta is an even function, cosine of minus n theta and cosine of n theta are the same. Therefore, it becomes like this, and cosine of, sine of minus n theta is identical with the negative of sine of n theta, since it is an odd function. Then when we add these two together, just to bring this expression, we have zn plus z to the power of n plus 1 over z to the power of n, cosine of n theta plus cosine of n theta, twice of cosine of n theta, but this will be cancelled. That is I sine theta, I sine n theta plus minus I sine theta will become 0, so that z the power of n plus 1 over z the power of n is equal to only twice of cosine of n theta will be left. Okay, question number 15. Given that p and q are real, and that 1 plus 2i, the root of the equation z square plus p plus 5iz plus q of 2 minus I is equal to 0. Determine the values of p and q, be the other root of the equation. So we are asked just to find the two equations here. So the solution would be, let z is equal to, substitute z is equal to 1 plus 2i here in the place of z here. Then it becomes p plus twice of k minus 13 plus I of twice of p minus q plus z, 9 plus is equal to 0. And then equating the real and the imaginary parts together, because the first expression closed by the first bracket is the real part, and this one is, that is 2p minus q plus 9, is the imaginary part, so that we have this equation, that is p plus 2k is equal to 13, because it is 0. 0 plus 0, that means 0 plus 0 I, that means, and 2p minus q plus 9 is equal to 0, or 2p minus q is equal to minus 9. So that if we solve this system of linear equation, we have p is equal to minus 1 and q is equal to 7. Therefore, if we substitute p is equal to -1 and q is equal to 7, this equation will be satisfied whenever z is equal to 1 plus 2i. And the other root of that is for p, the other root of the given equation could be sum of roots, that is the sum of the two roots. That means the negative of p plus 5i is equal to, which is equal to 1 minus 5i. 1 minus 5i. That is because p in this case is -1, so that if you substitute -1 for p here, -1 plus 5i, which is negative, when we distribute negative there, minus of -1 plus becomes +1 and positive 5 becomes negative. Therefore, the other root could be 1 minus 5i minus of, that's simply z. Its combination, that is z 1 plus 2i, which is equal to 7i. That is 1 minus 1 is 0, minus 5i minus of 2i is equal to -7i. Therefore, the other root of the previous equation. 16. Find z, an element of complex number, and plot the result in the argand plane, or that is the imaginary complex plane, if z to the power of 4 is equal to 1. That is the extraction of roots. Solution will be, we have for the extraction of root, we have the formula that is equal to cosine of 2k pi over 4, when 4 is the exponent here, and I times sine of 2k pi over 4 when k is running from 0 to that of 3. That's a random of, 0, 1 to 3, so that it will have 4 roots. Therefore, individually, when k is equal to the first one, that's simply 0. If you substitute k0 here, we have z naught cosine of 0 plus I times sine of 0. Cosine of 0 is 1, but sine of 0 is 0, so that z naught will becomes, I think, 1. Z naught is 1. And when you take k to be 1, if you substitute 1 here, it becomes z1 is equal to cosine of 2 pi over 4 plus I times sine of 2 pi over 4, or simply pi over 2 pi over 2. Cosine of pi over 2 is, I think it is 0, but sine of pi over 2 is 1, so that it is just z1 could be, there is 1, that is 1 times I, that is I. Similarly, for the second one, that's simply in order to determine z2, or the third root of this one, we have to take k to be the third element, that's simply 2. If we substitute 2 here, we have 2 times 2, that's simply 4 pi over 4, that is cosine of pi plus I times of pi. Cosine of pi is 0. Cosine of pi is, I think, -1. But sine of pi is 0, so that it is a real part, that is simply z2 is -1. And the third one could be whenever k is 3, it becomes, when k is 3, 2 times k, that's 6 over 4, or 3 over 2 pi plus I times sine of 3 over 2 pi. But 3 over 2 pi, sine of 3 over 2 pi is 1. And this one cosine of this value is 0. Therefore, it is purely imaginary. Therefore, it is z3, that is minus I. Therefore, the 4 possible roots of this equation could be 1i minus 1 and minus I. We know that, for example, here, I is the root of this one. It is complex conjugate, that is z3, which is minus I, is also the root of this one. The same holds true for z naught and z2. Then the plotting for this one could be that when z naught is this one, that's simply 1, purely on the real axis, and z2, it is positive I on the positive imaginary axis. This is I, and z2, which is -1 on the real axis, z2 -1 on the horizontal axis here, and the last one, that's simply z3, will be minus I on the negative imaginary axis. Therefore, there is a circle, that is a unit circle, whose distance for whose center is at the origin. That's simply the origin of the imaginary and the real axis. Okay, the next one, that's question number 16b. Again, it is similar to the previous one. Find z an element of C and plot the result in argand plane if z cubed is equal to -3. We expect 3 points or simply roots for this equation, and the equation will be obtained by using the previous formula. That the formula is twice of k. Z is equal to 2 times cosine of pi plus twice of k pi over 3 plus I times sine of pi plus twice of k pi over 3, when k is 0, 1, and 2. Then for k is equal to 0, we have z denote, that is, z denote is equal to cosine of the 0, that is pi over 3 plus I times sine of pi over 3. Cosine of pi over 3 is cosine of pi over 3 is I think 1, and sine of pi over 3 is radical 3. Therefore, the combination could be z denote 1 plus radical 3. And z1, that is when k is equal to 1, it could be cosine of, that is z1, 2 times cosine of this one, that's simply pi plus 2 pi over 3 plus I times sine of pi plus 2 pi over 3. And this could be, that is cosine of pi plus 2 pi over 3 is -2, I think -1, and -1 times this one, that's simply 2, could be -2, but sine of pi plus 2 pi over 3 is already 0, so that it is real, it becomes -2. Similarly, when the last one, k is equal to 2, 2 times cosine of pi plus 2 times 2, that is 4 pi over 3, which is 5 pi over 3 plus I times 5 pi over 3. Therefore, it could be cosine of 5 pi over 3 could be, that is, I think, 1 over 2, and sine of 5 pi over 3 could be negative radical 3 over 2. When we multiply both sides by 2, we have 1 minus radical 3i, so that we have 3 roots. These roots on the plot or simply in the complex or argand plane could be z naught is around here 1 plus radical 3i, and z2 is on the negative real axis, that is -2, and on the fourth quadrant, that is simply z2 is 1 minus radical 3i, so that this is the root of z cubed is equal to -8. Similarly, the last one, I think it is the last, that is, it is similar to that one. I think it's better if I left it as an exercise for you. By the way, the roots are here, but you are required to try to plot the roots on the argand plane. Okay, that is the end for the solution of